Scatter plots are great because they allow us to visualize 2, 3 and even 4 dimensions. However, every chart has a limitation. And how many data points are we actually able to plot in the scatter plots? So here's a visualization of what that quickly looks like. At the beginning we can still discern every single data point, but as they get more and more, we end up having a large blob of possibly overlapping data, which we cannot individually see at all anymore. So probably around here in the middle we have a problem that we need to solve. So one way that what we can do here is that we can go further by using transparent dots. So what do I mean by that? Instead of plotting a data point that is black, and here are 4 data points that are totally overlapping, which we cannot individually see anymore. Instead of a black dot, we use a gray dot with a black dot with transparency. In this case, it was set to 50%, which allows us actually to sort of have an impression that there are probably several data points already overlapping. If we now not use black, but instead gray, and gray with further transparency, we can see that this allows us to see deeper and deeper onto our page, and over time this little smiley that is hidden behind this data becomes visible. So this kind of illustrates the point that the more transparency and the more lighter your color of the dot is, the more data points you can visualize that are overlapping or very, very close to each other. However, even with transparency, you cannot salvage a plot that looks like this. What you then need to do is that you make summarizations of the data. So where's the mean? How is the distribution of the data, etc. Very often summarizing plots look like this in scientific papers. You have a bar that is not encoding actually a length, how we learned, how we got to know bar charts in the first place, but the bar encodes the average or the mean of a data distribution. So in this case, for example, category A has a mean somewhere around 70 or 74 and has an error range of plus or minus 3 or something like this. These plots are sort of got out of fashion 2-3 years ago because of what is illustrated here in this comic. So D says to C, sorry, we just can't trust you. Why does he say that? Because we can see that the error range of the C category is actually larger than the entire bar. So probably the lower level of the error goes beyond to the 0. So the distribution is extremely uneven and heterogeneous. Because people realize that a lot of data, the data distributions are actually quite hidden behind such plots, there was a big initiative to rule them out and to forbid them. So this initiative was called the Bar Plots Initiative, and the data that they showed to kind of illustrate this point was this. Their slogan was, friends don't let friends make bar plots. So these two plots, if they are summarized a lot, they look actually the same height and the same distribution. But wait a minute, if you plot the same data not as a bar chart, but instead as what is called a box plot, you can already see that while they are similar distributions, this one looks slightly different from this one. That should always, to the data detective in you, be a sort of a signal that there's something interesting happening that you should have a look at. And if you now plot these two distributions as a histogram in this case, you can see that they are wildly different. While the green data has a normal distribution, the magenta data actually has a completely different distribution from it and is sort of increasing with a higher numbers. So the scientific basis for this is, of course, that it is what's described in the Anscombe Quartet, and I invite you to really read the Wikipedia article on this. And basically, at some point, Anscombe realized that you can have a lot of different data points that all give you the exact same summary statistic values. So in this case, you can see that the R value is 0.81, 0.81, 0.81, 0.81, while the actual distribution of the data, you can see that they have nothing whatsoever to do with each other. So there are many ways how you can get a mean of 50, for example, and you have to be very, very careful what the actual distribution of the data below it is. There's also a nice paper from Tracy Weisgerber that illustrates this point for biology, but what kind of data this is really doesn't matter. So she used these two bar plots, and she showed in when you actually do not plot the summary statistics, but you plot the data distribution, you can see that the underlying distribution may be symmetric, in which case the encoding of the symmetric distributions for category 1 and 2 is actually faithfully represented with two bars. However, the data could also have exactly the same distributions, but one of them could have an outlier which is much higher, which would give you two bars of equal height. Another alternative is that the underlying data has unequal n numbers, so different numbers of points that actually contribute to the bars. And such a scenario is, of course, really, really unwelcome. You do not want to make comparison for a very large and a very small group, usually in summarizing statistics, which is why hiding that you have unequal n with two bars is very, very unscientific and unethical. And the most important to me is that your data could actually have a bimodal distribution. So by summarizing only the mean, you completely lose a perception of how the data is actually distributed. So this is assuming it has a normal distribution, but that might not be the case. For example, you could have scenario A and B and observe, for example, males and females, and they might have a totally different reaction to a certain drug, for example. By making a summary across all humans in your population, you lose out the very important information, maybe that there's a different, that you have two groups, man and female or something like this, in your data that react differently. So very, very important scientific information may be lost if you too quickly summarize the data. And below, Tracy Weisgerber just shows different kind of ways how we can also show the relationship between the two data points. So if they have actually a connect, if they display paired data. So over time, people campaigned enough against bar charts and summary plots. So by now, most journals forbid you to not plot the data and to summarize it like this. So what you will have to do when you publish a paper for most journals is to actually plot as much of the data as possible to your audience, to allow them to actually assess what you're showing. I quickly want to give you an overview of all the different distribution charts that exist at the moment, and they are increasing by the day. So each week I see a new version. So let's get a quick overview of what's currently possible. So what is advised at the moment in many fields is that you plot the raw data points. So in this, you can do this, for example, either with dots, with transparent dots, as you just learned before. The dots can be jittered, so they kind of wiggle along a line, or they can be very neatly arranged on a line. or you can display also the data points as a barcode plot. All of these plots allow your audiences to really see the actual distribution of the data. But very often you might want to help your audience to see a little bit how the data is distributed. So then there are two options. If you you can either focus on the center and the spread, or you can focus on the shape. And these two directions give your audience different information, or give you different information. If you focus on the center and spread, you can either show only the mean and the error range. You can show both. You can summarize a little bit with a box plot, but still show the data points behind each other, or you can exclusively show the summary statistics. You are not allowed to show this as a bar plot, as we just learned, but box plots, dot plots, etc. are absolutely fine. However, only focus exclusively on the center and spread if you have normally distributed data. How do you know? Well, you first have to plot the raw data in order to see if it is actually normally distributed. If your data is not distributed normally, then the mean is sort of completely useless to give as a value. And in that case, you better focus your audience on the shape. And then you can either show the actual shape of the data, you can show density plots such as a violin plot, you can show cumulative densities, or you can bin the data if you have simply too many and you want to group it somehow. In any case, if you focus on the shape, usually some transformation is done either by binning or by plotting the densities, and you need to learn about how to do that properly and faithfully to not hide any aspect of your data. So we sort of learned today that visualizing several aspects or several dimensions of your data set is possible, and there are very many charts that are actually suitable for exactly this purpose. For each of this data chart, you should know the limitations and the requirements for the data. So you should know what kind of data distribution you have and what kind of plot is suitable to show such a distribution. But in any case, you should never summarize data too early, because you might lose out on actually having an insight yourself. So at least in the exploratory step, please do not yet summarize your data.